and welcome to my presentation about the description of crack propagation in ductile materials under non-proportional loading conditions. This is the first part of this presentation series about modeling of deformation-induced plastic anisotropy. So the overall aim of our research is that we want to model fatigue crack propagation in ductile materials with the phase field method. But before we talk about phase field modeling, we have to talk about plasticity because we want to model ductile fracture. So this first part, I will be describing a new material model to include the effects of anisotropic hardening. Because this is important for non-proportional loading cases, as we will see later. And we want to define this new material model in a pretty simple, or in the most simple way in our opinion. The second part of the presentation, which is following, my colleague will be talking about the phase field extension of this plasticity model. So actually, if we determine yield surfaces experimentally, we can see three kinematics of the yield surface. So the first two, the isotropic and kinematic hardening, is pretty well known, and it's covered by a lot of material plasticity models. But you can also see a third kinematic, which is the deformation-induced anisotropic hardening. What it actually is, if we have proportional loading cases, we will observe that during this loading, the yield surface will start to shrink in the loading direction. And for non-proportional cases, additionally to the shrinking, we can see that the yield surface will start to rotate. So after this short introduction, I want to talk about the yield surface formulation more in detail. I will talk about some model properties of this plasticity model and how we calibrated our material parameters, and finish with a conclusion and outlook. So the idea is pretty simple and was already proposed in the 60s by Baltov and Savtsuk, where they introduced a fourth order anisotropy tensor into a von Mises yield condition. So you can see here the von Mises yield condition for the stress. We have our back stress, and we have this new anisotropy tensor H. This is the initial yield and our isotropic hardening. And to keep things a bit more simple and short, I'd like to introduce an effective stress eta, which is just the deviator of sigma and minus the back stress. So what we propose is we don't want to deal with fourth order tensors. That's not really convenient. So we want to decompose it in an initial anisotropy tensor, H0, which is constant, and two second order tensors. So with this, we just introduced one additional internal variable, a second order tensor, that should cover those two effects, the distortion of the yield surface and the rotation. We then assume that we don't have any initial anisotropy. So we have initially a von Mises yield surface. So this is just more or less a unit tensor of fourth order. If we introduce this decomposition into the yield surface, it simplifies. It might not look like, but it does, because we don't have any fourth order tensor anymore. We just have those second order tensors. And you can see if m equals to 0, so initially we don't have any anisotropy, we have the classical von Mises yield criterion. So how does this yield surface look like? We consider a two-dimensional stress state. So we have one normal stress and a shear stress. And as you probably know, von Mises yield surface is a circle in this stress space. It's shown in green here. And this new yield surface is an ellipse. So it's rotated and deformed. The semi-major axis has always the same dimension as the von Mises yield surface, but the semi-minor axis will start shrinking when the norm of m gets bigger. So the greater the norm of m, the smaller or the more elliptical shape this yield surface has. And because this angle lies in between the effective stress and this new anisotropy tensor m, we know that m must show in the direction of the semi-minor axis. So we want to model this in a simple way. What we want to do is we have an additive decomposition of strain into elastic and plastic parts. We have a normality rule, associated normality rule. For the elastic part, we have Hooke's law. We can define accumulated plastic flow rate. And we have the yield condition, of course. So plastic flow takes place exactly when F is equal to 0. We can extend this model pretty easy to consider viscoplastic or rate-dependent material behavior if we allow extra stress. So the yield condition can be greater than 0. And this extra stress should be the evolution for the plastic slip. But the interesting part comes now, because of course we need evolution equations for those internal variables. And for the isotropic and kinematic hardening, we take Chaboch's model or Armstrong-Frederick's model, which is written here. So we have this driving or this hardening part, and we have this recovering part. So we have a nonlinear evolution. And we wanted to model the evolution of the anisotropic hardening in the same way. So of course we have a different factor here, but this one is kind of the same type. So we have this driving part, eta. So M is evoluting into the direction of the effective stress. And we have this nonlinear part, this recovery term. And because we derived this model within thermodynamics, E has to be greater or equal to 1. So we can't have a linear hardening in this way. So how does this look like? What does this model do? On the left-hand side, we have a stress path or a loading scenario. We start in the origin and we have tensile load, compression, torsion, and so on until this very end point. And on the right-hand side, you will see a video soon. The red dot is the current loading site. The blue circle is the yield surface. So initially we have von Mises yield surface. It's a circle. And as soon as I start the video, you will see a green arrow appearing. And this green arrow shows in the direction of M. So we have this elastic region. Nothing happens to the yield surface. As soon as we arrive at the yield surface, M starts to evolve. The yield surface will start to shrink in loading direction. We get an ellipse. And as soon as we have this non-proportional loading and we reach the yield condition, the yield surface will start to rotate. And that's exactly what we wanted to model. And we will see that it kind of fits experiments as well. So now we reach the last point. Okay, so now we need material parameters, and we want to validate using experimental data. It actually is an optimization problem. So we want to optimize, or we want to minimize the distance of our model's yield surface to the experimental yield surface. And what we did is taking experiments from the literature from Ishikawa. He determined yield surfaces in thin-walled tubes where he subjected them to tension, torsion. And you can see one of those experiments here on the left-hand side. And you can already see that's not a circle. So that really is an ellipse during a proportional loading scenario. He took the stainless steel 304 and determined those 12 points on the yield surface for 17 different loading scenarios. And as you can already see here, this green dot, this current loading point, lies outside of the yield surface. And this is why we assume this is viscoplastic material behavior. So after our optimization, I want to show you just two results, two examples. For a proportional loading case, so we have combined tensile and torsional loading. And on the right-hand side, you can see the experimental determined points on the yield surface and our model's yield surface. And you can see it fits quite good. It's not perfect, but it's okay. And for the second example, again, we have this kind of complex non-proportional loading scenario. We can again see the experimental data, and the rotation of the yield surface is fit quite good, but the distortion is a bit underrated from our models. But you have to keep in mind that we optimized our material parameters for all those 17 experiments on the same time. So of course, not every single experiment is matched perfectly. So I want to conclude this talk. We derived a thermodynamically consistent material model where we introduced only one additional variable to address this anisotropic hardening. We can still address two effects, which is the distortion of the yield surface and the rotation of the yield surface. But I should mention that we want to improve the material parameter optimization. That's why we are currently doing experiments in our own group, because we only considered yield surfaces right now. But if we want to talk about material behavior and especially fatigue, we need stress-strain behavior as well. And we want to include stress strain, experimentally determined stress strain curves into this optimization as well. This plasticity or viscoplasticity can easily be extended with a phase field variable. And this is the second part of this presentation, which my colleague will be talking about. And then we are able to describe ductile crack growth under proportional but also non-proportional loading scenarios. So thank you, or thank the DFB as well for funding this project. Thank you for your attention.